Let's have a look at some first circuits. In spite of the many different kinds of components that you see out there, there's really dozens of different kinds of categories of electronic components. In this class, we'll largely only make use of about a dozen different kinds of components, and really nothing that requires more than really basic algebra to use. Now, the first thing I'm going to draw is sort of the basic hello world circuit. And it's going to be a light that lights up. And so first we're going to draw maybe say a 9-volt battery. And then we're going to draw maybe an LED up here. And we're going to draw something else called a resistor. And those usually have little color bars on them. And then, of course, there needs to be wires that interconnect these things together. And so here the resistor goes to the LED, one end of the LED goes to the battery, and then the other side of the battery goes to the resistor. And so notice this, of course, makes a circuit, or rather a complete circuit, meaning that everything is in a loop. One of the other things that we should note is that the components themselves have polarities to them. And so there's a negative side of a battery and a positive side as well. There's a negative side of a LED and a positive side, and so on and so forth. So this is not a great way of conveying circuits for a variety of different reasons. Number one is that it's basically not portable. You can't really give this to anybody else, assuming you have a circuit that's more complicated than this sort of LED circuit, and have them really understand what's going on. It's also really sloppy, which doesn't say anything about my drawing skills. To help address this, there's a convention that we use that's been around for a very long time, I think over 100 years, called the circuit schematic. And there's a series of canonical ways of drawing circuits that allow us to convey what the circuit's doing and allow other people to read it and allow us to sort of look through it and debug it together. Rather than it being sort of an artistry, it becomes an engineering discipline. And so to draw this a little bit better here, the battery is represented as this symbol. Again, each component here has a symbol. And then maybe we go from the battery to the resistor, and then maybe we go from the resistor to the LED here. And the LED has a lightning bolt on it that I always like to draw. Never very good at my lightning bolts. There we go. So there's other parts of the schematic that we really need to include. One of the central components is the labels for each of the components. And so this sort of squiggly line over here is a resistor, and so we give it a character representing it for resistors. That's that's R, and then a number, and this is the first and in fact only resistor that we have in this circuit. The batteries are usually represented using BAT, and again we only have one here. And then an LED, you might think that that would be represented by L, but if you think of what LED stands for, it stands for light emitting diode. An LED is a special kind of diode, and a diode is a class of components. And so we call these, excuse me, we call these diodes. So D, and in this case, 1. So we have a battery, we have a diode, and we have a resistor. And in fact, maybe we'll draw a slightly better resistor here since that one's kind of wonky. 1, 2, 3, there we go. It's kind of a funny schematic here, or kind of a funny symbol rather on a schematic that it might have. And then sometimes we also draw just sort of for our own help, especially when we're sort of new to this, what the values of the components might be, or what the polarity of the components might be, or whatnot. And so, particularly for the battery, this is the positive side of the battery, this is the negative side of the battery. This is the negative side of the diode, this is the positive side of the diode. And then over here, our resistor is not polarized. That means it doesn't have a positive or a negative, so not polarized. Okay. So we have our first three electronic components here. We have a battery, we have a resistor, and we have an LED. And so what might we expect this circuit to do? Well, this is something that you probably learned already in grade school or high school. This will light up the LED. But what do each of the components do in this really simple circuit, right? Well, you probably know that already. So the battery supplies power to the circuit here. It gives us power. That's kind of easy. The LED, that's pretty easy too, right? We know that that generates light. The resistor, what does this thing do? You may or you may not know that yet. And technically we actually have a fourth component here that you might look at this circuit and wonder what it is. The fourth set of components, in fact, are the wires that interconnect the different components here. And they're non-trivial to consider, but in fact, most of the time we just don't consider them in most of the circuits that we're going to be creating in this class, just because their various properties like resistance and whatnot are extremely small compared to other circuits. So to ask the questions of what these do and how they interact and how we can build circuits out of them, we need to learn about three fundamental aspects of electronic circuits, which is voltage, current, and resistance. So what is voltage, what is current, and what is resistance? These are things, again, that many of you probably have heard of before, but we don't really understand them until we really work with them a lot of the time to get a sense of how they work. A circuit sort of physically is a flow of electrons from one position to another position. You can sort of imagine a wire here, and we might have some electrons that are sort of flowing down it a little bit. And so the question is, how do voltage, current, and resistance sort of relate to the idea of electrons, and how do we use them? So you can sort of physically imagine this flow of electrons like a river that flows maybe from one city to another city or something like that. And so if we imagine this river here full of electrons, the current is, I always like to think of it as sort of how wide the river is, sort of how much you have. So current is how wide our sort of river is here. And maybe to make sure that we know it's a river, we'll draw a little bit more water here with our little electrons flowing through here. Now voltage then, what on earth is voltage in this analogy? Well, voltage is how fast the water is flowing here. So that would be voltage. And then what on earth is resistance? Well, at least the name gives us a little bit of an intuition about what resistance might be. You could imagine that there might be a bunch of rocks in the river somewhere that sort of obstruct the flow in some way. You can imagine resistance as analogous to how much friction there is in making the water move, or how much we restrict the flow or limit the current here. So in our simple LED circuit, we have two kinds of components that we can think of here. And I'm going to give away what we're going to talk about here a bit. with our heading, Kirchhoff's voltage loop law. So we can consider that in an electronic circuit there's two kinds of components. There's components that generate power, and there's components that use the power, that do things with the power. Whatever that means, right? So Gustav Kirchhoff, who was a German scientist, was really trying to understand the foundations, the mathematical foundations of how electronic circuits work around 1845. And what he found is this really simple but sort of really foundational concept of circuits, and that it's basically that the amount of power that we generate, power generated, has to be equal to the amount of power used in a circuit. So if we generate, say, 9 volts from a battery, then the circuit has to use 9 volts somewhere in it. Which is to say, to make the voltage sum 0. So you can imagine rewriting this a little bit and saying 9 volts generated minus 9 volts used is equal to 0. Essentially here what we're trying to do is we're trying to make the voltage sum, the sum of generated and the sum of used, be equal to 0. And so in our simple circuits where we have our battery, this is a terrible battery. Have to have some standards here. So in our simple circuit with a battery and an LED and a resistor, if the battery is generating 9 volts, then the other components here, the resistor and the diode, or the LED, have to be using 9 volts somehow. Slightly more formally, that basically means that the sum of voltages in the circuit have to be equal to 0. So let's imagine a slightly more complicated circuit that has 4, or rather 3 resistors in it. And let's call them, what are we going to call them here? Let's call this one R1, R2, and R3. And then of course we have our battery, which we'll call BAT1 here, though that's not super important, the labels right now. And then each one has a voltage associated with it. And so say the voltage for the resistor number 1, the amount of voltage that it uses might be V1. And over here for resistor 2, it might be V2. For resistor 3, it might be V3. And for the battery, it might be V4. Again, this one is generating voltage, and the other 3 are using that voltage. And so what Kirchhoff's voltage loop law basically says here is that the power, or the voltage rather, generated by the battery minus the voltage used by resistor 1 minus the voltage used by resistor 2 minus the voltage used by resistor 3 has to be equal to 0. You might ask yourself why on earth this might make sense, sort of physically. And the way that I like to think about it is that if this wasn't the case, if the amount of power generated in the circuit was different than the amount of power used in the circuit, because the circuit sort of flows around in a circle, if you had leftover voltage by the time you got to the end, say here, then you would basically be adding more power into the circuit every time the electrons float around. And so it would basically be sort of like a perpetual motion machine or an infinite feedback loop of voltage, which would be fun, but unfortunately that's not the way that physics works. So back to our really simple example here. And in fact, we're going to make an even simpler example where we just have a battery and an LED. By the way, sometimes I forget my lightning bolts, so there we go. And so let's say that's 9 volts. So we're using a 9-volt battery, and we know that that's generating 9 volts. That's sort of given to us. And so we know by Kirchhoff's voltage loop law that the rest of the circuit must use 9 volts as well in order to satisfy this criterion. The problem here is that components have physical limitations on how much current they can take, right? Physical limitations. And I'm going to draw that in red. To remind us how important that is. One of the reasons why we need to remember that that's important in electronics is that if they have physical limitations on how much voltage or current they can take, when they exceed those limits, they usually end up exploding or at least breaking, but sometimes exploding. And so how on earth do we know when something's going to go boom or not? The basic idea is that in general, as we increase the voltage on a part, so as the voltage goes up, other things go up as well, in particular current. So as voltage goes up, current usually goes up as well. And so if you give something too much voltage, the current is going to go up, and usually if the current exceeds the expectations, the part blows up. Returning to the water example, that's sort of like the water, or increasing the water so much that eventually it's going to be too much for the riverbank to handle and it just sort of flows over. So then the question is, how do current and voltage relate? And I like to look at this in the context of an LED. So how on earth do current and voltage relate? I'm going to draw us a graph here. And on one axis of the graph is going to be the current. And we're going to measure this in milliamps. So this is a small amount of current. And on the other axis, we're going to talk about voltage. In this particular case, it's the forward voltage of the LED, which for our purposes, we can sort of think of as the amount of voltage that the LED is given to use up, given to absorb, and convert into light or heat or something. And so what on earth does this graph look like in general? Let's give some numbers to the graph as well here. Maybe we have 0 volts and 0 milliamps, and then we have maybe 1 volt, 2 volts, 3 volts, 4 volts, and so on and so forth. And then here I'm just going to draw ticks. So this will be, let's do these every, say, 100 milliamps, so 200, and then this one down here is 100 milliamps. And so the graph is really interesting. in the following way. Let's give ourselves some ticks here. So as you give an LED increasing amounts of voltage, what's going to happen? The graph tends to look like this. The current basically lives at 0 for the entire time, and then it just kind of rapidly goes up here. The squiggles are mine. And so what's going on here? Why is this graph basically kind of look almost like a step where it suddenly shoots up really quickly? And what's the ideal voltage for an LED then? In general, for most of the LEDs that we'll end up using in this class, and most of sort of the common LEDs that you end up observing, they have a maximum rated current that's somewhere around 20 milliamps. That's not very legible there. 20 milliamps. There's also a lower limit on the current, which tends to usually be anywhere between 1 to 5 amps. And so if we actually were to zoom in on this little section here, you would see that there's a spot somewhere between 1 to 5 milliamps. That's the lower bound for lighting up the LED. And then there's an upper bound that's generally around 20 milliamps. It can be a little bit higher, a little bit lower for most parts, where it's generating the most light it's ever going to generate in a safe capacity. And it's using the most current that it can really use in a safe capacity. And then what happens here? Well, up here is, and we could really sort of think about this drawn maybe a little bit more specific here with a little bit more resolution. So the current kind of goes up a little bit nicely here, and then the current zooms up. And so what you basically can think of this as is that this bit here is the operating regime of the LED, where at the bottom side here it's starting to generate light, and at the top side here is where it's generating the maximum amount of light that it can safely generate. If you give it more voltage than usually somewhere around here, and so in this particular theoretical LED, that would be around 2.7 volts. Then it starts to rapidly use way more current than it can handle. And this is basically the boom case, where the part is just absorbing absolutely too much energy. Whereas this regime here in this circle is sort of the happy regime, where it's using exactly as much as it needs to be sort of an operating characteristics. And then over here is sort of, it's not really doing anything because it doesn't quite have enough voltage yet to generate any light. And so again, there's this sweet spot here in the middle where it's generating enough light that it's going to be seen by somebody with eyeballs like you and me without blowing up, but it's not got too much current to just sort of explode, and it's not got too little to not generate anything at all. And even though I've sort of drawn a sort of cartoon number here of 2.7 volts as sort of this magic number here, in practice, the forward voltage has a range, and the range tends to be anywhere around 1.8 volts to 2.5 volts, depending on the kind of LED that you're using. In fact, one of the things that makes this vary the most is what kind of color you're talking about. And so LEDs that are red They are some of the oldest LEDs, and we're very good at manufacturing those, and so they use very little power to generate their light, and so those tend to have forward voltages around 1.8 volts. Again, this is just a general rule. Green ones are also pretty old, and so those ones tend to be maybe slightly higher, but still pretty low. Blue LEDs are reasonably new in the world of electronics. They're, I don't know exactly when they were invented, but they use a slightly different process, and so they tend to have pretty high forward voltages still, sometimes around 3 or even 3.3 volts to really get them to light up. So in practice, you basically have to either look at the data sheet, which is a document that describes what the forward voltage for the LED is, that has usually a curve that looks something like this. Or you just sort of have to empirically check out what you think it's going to be by slowly ramping up the voltage and seeing how the current works with it. And so, sort of looping back to Kirchhoff's voltage loop law here. So we know that we have a power source that's generating 9 volts, and we know that we have to have our components absorb 9 volts. But the problem is that our LED here can't absorb more than, say, 2.5 volts, right? Just to give a nice round number to work with. And so what on earth do we do here? How do we handle this? And so you've probably guessed what that might be. And the answer is basically the resistor. And that basically leads us into talking about Ohm's law. So Ohm's law says that the current through a conductor, and current is usually I, is related in some way. It's proportional to the voltage through the conductor and the resistance across the conductor. And we can draw our triangle with V, I, and R. Most of these are pretty voltage, resistance, and current. And we can get our common forms of this. So if we want to know voltage, we need to multiply current times resistance. If we want to know current, then we do voltage over, we do voltage over resistance. And if we want to know resistance, then we calculate voltage over current. A note on units here. So current is usually measured in amps, or A. How many amps is a lot of amps? In this class, generally the maximum we use is about 1 amp total, and most of our circuits usually take somewhere between 20 milliamps and 500 milliamps. So milliamps is sort of going to be our common unit of measure here, which is MA. Voltage is usually measured in volts. How much voltage is a lot of voltage? Well, in class, most of the circuits we're going to be making will be powered with 5 volts from the USB port. Most electronics run at either 3.3 or 5 volts, and computers, sort of the ones that you have on your desk, usually use a variety of different internal voltages. CPU usually runs at 1.8 volts, 12 volts historically for motors and the hard drives and other sort of heavy things. But in general here, nothing that we're going to use is going to be much more than 5 volts. And resistance is usually measured in ohms, and the symbol for that is omega. And oftentimes the resistance that we can, or the resistances that we consider here, sort of have the most range of anything that we're going to look at. We're going to look at anywhere from a few ohms to many kilo or mega ohms. So if you imagine going from 1 ohm to 1 mega ohm, that's quite a range. So let's look at an example of using Ohm's law here. And we won't belabor this too much. So imagine that we have a resistor, and there's a resistor, and imagine that the resistance of that resistor is 5 ohms, and imagine that the current going through it is half an amp, some nice numbers. Then what's the voltage that is going through here? And so we know that voltage is equal to current over resistance, which is 0.5 amps times 5 ohms, and that's going to be 2.5 volts. Some nice easy numbers. Now, I told you that we don't consider the wires a lot of the time in a circuit, and that's because wires usually have very low resistance. Wires have low resistance. Generally less than an ohm. A lot of the time they're quite less than an ohm. But every component has a resistance in a circuit, including the battery, or including the wires, even though it's very, very low. And so if you short out a battery, you're essentially connecting the battery with a very low valued resistor. And so you can think of what that does to the current. So if you imagine having your 9-volt battery here, and you're just literally connecting a wire between the two, you already know that that's bad news, but why is that bad news? Well, again, you're basically doing this, except remember, the wire itself is a resistor, so you can model that as this. So then the question is, what is that going to do to the current, right? And so why don't we just pretend that the resistance of the wire is very low. Say it's 0.001 ohms, and say this is a 9-volt battery here, so our voltage is equal to 9 volts. What on earth is our current going to be? Well, it's going to be equal to the voltage over the resistance, which in this case is going to be equal to 9 volts over a very tiny number. And of course, that means that we're going to generate an absolutely enormous current, probably very briefly, because the wire is either going to melt, or your hands are going to melt, or some other terrible thing is going to happen. And so that's why we don't short things out. And then maybe one more quick example here. What about a 1,000 ohm resistor, and it has a voltage of maybe 6 volts going through it? What's going to be the current? That's going to be 6.5 volts over 1,000 amps, and so that's going to be about 6.5 milliamps. So you can probably see where we're going here. We need to use Ohm's law to solve for the resistor in our circuit. And why? Well, we have, let's sort of recap here. here's our circuit with our resistor. I swear I get worse at drawing resistors every year. 1, 2, 3, there we go. We have a resistor, we have our LED, we have our battery. And so we know that the battery is generating 9 volts. We know that the LED can only take about 2.5 volts. And again, that depends on what you're setting it to. And so we have some voltage left over that needs to be absorbed somewhere, right? And so with 9 volts generated and 2.5 volts being used so far, we need to have something else use 6.5 volts in order for the LED not to blow up. And so that something is basically going to be the resistor here. We need to calculate a resistance so that this resistor uses 6.5 volts. That allows us to essentially set the voltage of the LED and generate a particular amount of light. And so you can imagine if this is 2.5 volts and this is the amount of light you want to generate, it's going to take that amount of current to get to. Okay. Let's erase that. Okay. So what if we substitute in a 1,000 ohm resistor into our circuit just for fun here, just to have an example? Well, that's going to set the current of the circuit to 6.5 milliamps, as we just saw up here. Now, the current we know needs to be somewhere below 20 milliamps, as in our graph here, we know that 20 milliamps is about the maximum that most LEDs are ever going to take. And so if we set our resistor 1 to 1,000 ohms, then we know that the current of the circuit is going to be about 6.5 milliamps, because we just happen to figure that one out up here. And so that's going to generate a certain amount of light. It's going to be somewhere in the middle. This is slightly above the sort of bottom range of an LED, and it's not anywhere near the top of 20 milliamps. So it's going to be some medium amount of light that comes out of the LED. Brightness is proportional to current, and so that's why we care about the value that we set here. So the higher the current, the brighter the LED is going to be. Typically, we want to select the LED current beforehand so that when we're designing a circuit, we have a particular brightness. So let's think of another example here. Let's go through one more example here. Let's have our 9-volt battery. Oops. Let's have a 9-volt battery. And instead of using a forward voltage of 2.5 volts, let's use a forward voltage of 2 volts. And let's set the desired current. We want the current of the circuit to be 15 milliamps. And so the question is, what resistor value do we need for the circuit? And so we can think about it as sort of a two-step problem. Number one is that we have to figure out how much voltage the resistor has to absorb. And so if we're generating 9 volts and the LED is using 2 volts, then we still have to absorb 7 volts, or more specifically, our resistor has to absorb 7 volts. And so then step 2, we know that resistance is proportional to voltage over current. And in this case, the resistor value, or the resistor is going to have to absorb 7 volts of voltage, and we want to set the current of the circuit to be 15 milliamps. And so 15 milliamps is 0.015 amps. And so if you calculate this out, you end up getting a value of 466 ohms. A pragmatic note here is that in general they don't manufacture resistors of any value. At least that used to be the case. It seems like these days you can get almost anything. But there are standard values of resistors, and so usually you go up a little bit or down a little bit to a standard value. And so in this case, the nearest standard value would be 470 ohms. And so one of the things that you usually have to do is you have to do the backwards calculation then and say, okay, if I substitute in a 470 ohm, the current's going to change a little bit. Is it still going to be within an acceptable value? And usually it is.